handwritten notes to get your studying on board. It will be about mass spring systems, undetermined coefficients, and Laplace transforms, and then this AY double prime plus BY prime plus CY, which is the mass spring equation. So we're going to have a quiz and an exam. Yeah, so the idea is that we'll take the short quiz at the first part of next week, and then the exam is set up for Tuesday. And it'd be a good idea for you to take a look at that quiz before the exam. Okay, so announcements aside, what are we going to do? We're going to do Dirac functions today. We're going to review step functions first. We're then going to get into the definition of what the Dirac function is, at least as much as we can get. The Dirac thing that we're going to look at was made by physicists, later made rigorous by mathematicians, and so it's a kooky thing. And when I say functions, and I use the air quotes, it's because it's not really a function. It's the limit of a sequence of integrals that converges to this thing that we want to have a certain behavior with. So it's going to be a little weird that way, but usage, not bad at all. And then if there's time, I'll do some linear algebra, which is the next phase of the course, not what's going to be on the test, not testable material, but we're finishing with testable material right now. Okay. So are we allowed to have the Laplace transform sheet on the exam? Definitely, and that does not count for your 1 page of study guide, handwritten notes that you're expected to bring in, both as a means to study and solidify the concepts, and to have a utilitarian tool, and you'll have the Laplace transform sheet. So if you check out the external drive, this is what we've got going on. So let's have a little recap of step functions. Remember, we defined a step function to be a mathematical switch. What do I mean by that? This is a function that's going to be 0, and then at some point in time, it's going to become the number 1, and then stay the number 1 for all time. So it has this binary nature and a time at which you set that off. Okay. We use the function u to represent the unit step function. The unit step function will go from 0, jump up to 1, so it's like a step, right? And this a parameter right here controls the horizontal shifting of that step function, right? So that I can position that step to be at a certain location in time, and that location is at a seconds. I can take the Laplace transform of this, and I get e to the negative as over s. This is probably not the transform that we go to most frequently, because the step function turns on and off other functions, right? But what we want to note from this, which I'll highlight in red, is the emergence of this exponential function in Laplace side. We want to know in our procedural thought process that when you see exponentials in the Laplace domain, that is telling you about step functions in time. Okay? What sort of things are happening in time? Well, odds are you'll have a step function multiplying another function, f of t, right? In this case, if I look at table entry number 5, the table says if you have a step function that's triggered to go off in a seconds and a function f that's been horizontally shifted a seconds forward in time so that it blasts off at a seconds along with that step function, then the Laplace transform of this stuff right here will be e to the negative as. Again, the exponential is like, yo, there's a step function in the time domain. And then the Laplace transform of f. So what did we call this Laplace transform of f? That is what we've been calling f of s. This is the formula that you use to go from s's to t's. And it tells you about time delayed functions in the time side. Okay? So that time delayed function is totally what we want to do here, because it's like, what is this thing doing? It's doing nothing. It's doing nothing. I hit it, and now it's becoming sinusoidal oscillations that have waited to that moment where I hit it. Right? So odds are this is the type of formulation we're going to see when we're coming back from the S domain. But sometimes you might want to take functions forward in the time domain, from the time domain into the Laplace domain. And so you have number 5 alternate. And in number 5 alternate, the step function here is triggered to go off at a seconds, and it's going to fire on the function g of t. And notice that g of t has not been horizontally shifted. The reason for 5 alternate is that if you just assemble some stuff in the time domain, odds are the functions aren't shifted horizontally just right for table entry number 5 to work. Okay, but that's why we have table entry number 5 alternate, which says, yo, the step function, that's gonna read like, it's not exactly an exponential in Laplace space, but you will see it give rise to an exponential. That tells you about the moment in time where things trigger. And then you'll take the Laplace transform, not of g, but g of t plus a. Okay, and so this is used to go from t's to s's, and then we shift first, then transform. Okay. So that's the idea with step functions. I'm going to check out the question in chat, and then feel free to ask any other questions. I'll give some time for that, and then we'll move on to what this Dirac function is. Kelsey in chat is asking, how do we know when to decide when t minus a will be instead of a t, or instead of a t inside the function when using 5 and 5 alternate? For 5 alternate, it's set up with g of t right here, because what this g of t is doing is it's being a placeholder for all of the not step function stuff in time. Okay? So you figure out what all of that not step function stuff is in time, you shift, and then you transform with the Laplace transform in the table. Okay? So here, you don't really have to worry about whether or not on the time side it looked right, because you force it into this t plus a form here, and then transform. Now coming back from the S domain to the T domain, that process is reversed. You see the exponential, you gather up all the stuff that is not that exponential, which is a placeholder f of s. Then from capital F of s, you get little f of t, and then you shift that little f of t. So the shift is always something that is forced on you by the table, and it's not something you got to try to magically see. You just use the placeholders and then perform the shifts when the table tells you. Can we do a lot of step function work in recitation tomorrow? I'll let the TAs know that you said that. I think that they already know step functions, they take a bit. But once you get familiar with them, they work out. And the examples that we'll do today will hopefully help that out, but in a mass springy sort of way. Any other last questions before we get into this, what some mathematicians might call an abomination? But it's been made rigorous over time, so it's cool. Okay. So the Dirac function, functions in quotes. The following is a generalization of the notion of function, right? So physicists made this in around like late 1800s, early 1900s. Mathematicians were like, oh my goodness, this thing can't be real. And it is mathematically funky, so they treated it rigorously, right? So it generalizes the notion of function. It needs to use calculus to get defined, and we call it the Dirac function or distribution. Function is an abuse of the term. It's not actually a function. It would be formally called a distribution, but don't worry about the esoterics. These are the 3 things that we will require. Thing 1, delta is going to be the name of the function, just like u is the name of the step function. Delta here is the name, and it's going to be t minus t naught. T naught plays the same role in a and allows me to shift this thing horizontally in time. Well, what is this thing? This thing is the number 0 whenever t is not equal to t naught. What does that mean? And T naught is expected to be a non-negative number. What does this mean? Over here, if you look at our little graph, let's say that's the horizontal axis is the time axis. I'm going to put a little T naught on that time axis. And so, what is this function doing in time? Well, it's doing nothing, 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 nothing. And then at T naught, no one's really told me what it did. And then after T naught, it's going to be nothing, 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 nothing. So outwardly, it's behaving exactly how we want because it is nothing, 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 T naught, nothing, 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 nothing. Okay? So that's the idea. Here's the kooky part. Thing number 2, rule number 2 that I want this object to obey is that if I integrate from 0 to infinity, meaning I accumulate the area under the curve in the right half plane of this delta function, when I perform that accumulation of area under the curve, I want that area under the curve to be the number 1. Okay. And this is something that's a little more fun in the live setting because you turn around and you recognize it's 4 o'clock in the afternoon, certain people are in, certain people are out. Yeah, right. And then certain people have the reaction that's coming in on chat, which is, yo, dude, you're not accumulating jack for area under the curve. And you'd be right. You'd be absolutely right. But it's the rule, and I'm just going to follow the rule. So you might ask, if there's no area under the curve, and then at this point, something funky happens, and then there's no area under the curve, what is this thing doing that gets me no area under the curve, or 1 unit of area under the curve in that little moment? Well, some books will write the following, and I don't. I'll draw it. Whatever's going on here must be going crazy. And books will say, oh, at that point, it takes on infinite value so that line segment has area, which, I mean, so like none of this is working out, right? It doesn't make sense. It can't make sense in this way because it's not really a function, so I can't draw it like a function. But that's the idea. Right? What you could picture instead is picture like the bell curve, right? Only you make the bell curve really, really narrow, and the peak of that bell curve starts going up and up and up. And this is the idealization that the width of that bell curve went to 0. And then the height went to infinity. And somehow in that limit, we got 1 unit of area under the curve. Still, it's not satisfying. I get it. So, going back to the bowl really quick, right? It is an idealization of this, because when I hit it, that hit, it takes place very quickly, but it's not instantaneous, right? I mean, what is instantaneous? Like, it doesn't even make sense, right? We're in philosophy here. This is esoterics. The third property, which we'll get into the esoterics a bit more, but is the important property relative to the Laplace transform, is this sifting property, it's called. And so I'm going to integrate from 0 to infinity this delta multiplied by f of t, and then I need to integrate with respect to something, so I'll integrate with respect to time. So there's my dt. And here's the idea. If the delta is 0, except when t is equal to t naught, then I can find this area under the curve by just figuring out what the integrand is doing when t is equal to t naught. Right? Because all of this, okay, let's draw it. I can draw a little bit here. It's not too funky. Let's call this f of t function a green function, and let's draw it over the same graph. Here's my f function. Okay. Now, this f function is a collection of a bunch of different heights, right? And those heights are getting multiplied by the purple function, and so they're just being suppressed. Except at this one point where my cursor is, that is the only height out of all of the heights in the f of t function that I'm even going to notice. And so I'll just circle that in with a green highlight. That is f of t naught, the height when t is t naught. But now here's the game, and here's the absurdity of it. Since t naught's some number, say it's like the number 2, f of 2, if this were a 2 right here where the cursor is, that doesn't depend on t anymore, so you could pull it out of the integral. And if you pulled it out of the integral, you'd have f of t naught times the integral from 0 to infinity of delta t minus t naught dt. But then what did you define this integral to be? You defined this integral to be the number 1. So what comes out of this integral is just f of t naught. And that's what this thing is and does. That's the kookiness. If you want to think about the kookiness physically, it is this. You've got this curve in space, which is the green f function. That curve is one-dimensional because it's a curve, right? If you straighten it out, it'd be a line. A line's a one-dimensional thing. What this delta function represents is the idealization that you can go in with your zero-dimensional tweezers and pluck out a single point out of the one-dimensional curve. Of course, we can't do that, but we'd like to idealize that for STEM purposes. How did this function come about? It came about because at the time when the physicists were dealing with mathematical fields like electromagnetism, stuff like that, they needed objects to represent point sources of charge and mass. This is the object. But what is a point of charge or a point of mass? What is a point, right? Like, those things don't actually exist, except in our minds, right? So, there we go. Funk factor is on high. What we really care about now is, that's great. My mind's bent. How do we use this thing? And that's what we're going to do next. So, does f of t equal f of t naught? Here, f of t only equals f of t naught because this delta function here is going to be 0 for all other t values. So this is more akin to the statement of all the different f's, I only care about the one when t is t naught. Yeah, right. If I ever were to just like suddenly up and quit a job, a lecture like this would be the way to do it, right? Come in, talk about stuff, make it barely even seem true, and then just never show back up again. So I'll see you on Friday. All right, so I'm going to freeze the screen. You can take any last notes you want. And now we're going to get an idea of how this thing is used, which is really what you want to see. All right, so I'm going to come back in 3, 2, and 1. So I'm going to put the 2-minute timer up on the board, and what I'd like you to do is I've copied the Dirac. Oh, wait, let's talk about that really quick. What we want to know now is what is the Laplace transform of this delta? Well, that is equal to the integral from 0 to infinity of delta t minus t naught, the thing I'm transforming, times e to the negative st dt. But since this delta is going to be 0 for all values of t that are not t naught, the only time I even care about t is when t is equal to t naught, so I have the integral from 0 to infinity of delta t minus t naught, e to the negative st naught dt. Remember, t naught's a number. That's the point it's in time where things spike up, where the hammer hit happens. But this exponential can just be factored out front, leaving behind the integral of the delta. But the integral of the delta is the number 1. So this leaves us with e to the negative st naught. Which totally makes sense, right? The Laplace transform of the delta is an exponential, because what does an exponential tell us in Laplace side? It's telling us that something's going to happen at a specific time. Well, why would that be? If I do delta, nothing, 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 hit, back away, well, something's going to happen at that T-naught moment. It's me hitting this thing, and then the thing will ring. The singing bowl will ring and oscillate as a consequence of the energy that I've provided it. Okay, so now I'm going to put the 2-minute timer up. I'm going to scroll down, and I'm going to ask that everybody take a swat at this second order ODE, and then we will work on seeing how it comes back to the time domain. And I'm going to leave for 1 minute. I'm in desperate need of water. All right, let's start back up. So, same rules as always. I'm going to take the Laplace transform of the whole equation. When I take the Laplace transform of the whole equation, I use table entry number 2 to transform the second derivative to pick up 2 s multiplications, capital Y, and some initial conditions. And then I have adding that to 5 times table entry 1, which is s times y of s minus y of 0, and then plus 6 times y of s. I know more. I know my initial conditions. Y of 0 is 0. Y prime of 0 is 0. And so, all those initial conditions vanish, leaving behind just my capital Y functions with some coefficients. But if I factor those capital Y's off, I will be left behind with s squared plus 5s plus 6, which is the characteristic equation. Okay? And then what is that equal to? On the right-hand side, this is equal to the Laplace transform of delta t minus 2. But table entry 19, which I have hanging out right here, says, yo, you transform the delta function, you just pick up a single solitary exponential. So that's e to the negative s times 2, or I would write it as e to the negative 2s. And maybe what I'll highlight in pink here is that this 2 is being carried around in the pink way. That's where you see it, highlighted in pink. So now, if I want to solve for capital Y of s, I have e to the negative 2s over s squared plus 5s plus 6. And then, since maybe we're already seeing this coming, that's our characteristic equation. Let me just factor it because it has real roots into s plus 2 times s plus 3. Okay. All right. Question. As a mass spring system, what is the initial displacement of the mass? Would be 0, right? What's the initial velocity of the mass? It would also be 0. So if you had this mass spring system, here's the y equals 0 state, and you have this mass spring system, and at time 0, it's right here, and it's not moving, well, what would be your expectations for that mass spring system? Well, it should do nothing, right? It's not moving. It's already in the configuration, the static configuration, so it would just sit there, okay? Now, what's going to happen is because of this external force, in 2 seconds, you're going to thwack it with a hammer. And once you thwack it with a hammer, it's going to do its thing. What is its thing? Is this a damped mass spring system? Is it, if it is damped, is it overdamped, underdamped, or critically damped? And how might I tell? Well, I'd look at the roots, right? The roots of the characteristic are going to be characteristic equation are going to be real, different. So what did we call it when the roots were real and different?
I thought that S was imaginary, though.
S is complex, which is like everything, right? Imaginary and real parts, covers them both. Yeah. It has the capability of being purely real, purely imaginary, or a real plus an imaginary. Okay. So this is an overdamped mass spring system. Overdamped mass spring systems are not going to oscillate, right? It's pure exponential decay. Now we want to get that feeling in our head as we see this come out in the Laplace side. So forget about the mass spring thinking. I'm in the Laplace side, I see an exponential. Seeing the exponential triggers me into using table entry 5. Right? I see that exponential, I say, oh, this is table entry 5. How do I work table entry 5? I've been told to work table entry 5 by taking the exponential, setting it out front, and then leaving behind everything that is not that exponential. Everything that is not that exponential is what we call capital F of S. Now the table says, yo, you've got capital F of S. What I need from you now is little f of t. Now, ultimately, I'm going to shift little f of t, but I still need to find little f of t. So from capital F of S, what I need to figure out is little f of t, and I want to be thinking that this is overdamped. Since it's overdamped, I need to be thinking about table entry 12 and exponential functions. And to see those exponential functions, I'm going to have to bust out a little partial fraction work right here, right? So I'm going to say that 1 over s plus 2 times s plus 3 is equal to a over s plus 2 plus b over s plus 3. But then again, that is equal to combining the fractions a over a times s plus 3 plus b times s plus 2 all over s plus 2 times s plus 3. And now, if the denominator on the right is equal to the denominator on the left, then I set their numerators equal to one another. And so I can just read off, this is like not the worst partial fraction we've ever seen in our lives. I can just read off the numbers. If s is equal to negative 2, then the b term goes away. And if s is equal to negative 2, I have negative 2 plus 3, which is positive 1, times a is equal to 1. So a must be equal to 1. And now if I choose s is equal to negative 3, the a term goes away, and I have negative 3 plus 2 giving me a negative 1, times b is equal to 1, and my b must be equal to negative 1. So I know my a's and b's, and so y of s is e to the negative 2s times 1 over s plus 2 minus 1 over s plus 3. When I look at these two functions right here, I see table entry 12. So I see table entry 12. I see these exponentials in the Laplace side, which is copacetic with the fact that I've observed that this is an overdamped mass spring system. I'm feeling the exponentials from that. Now I've got to scoot this y of s back over to the time domain. So I take the inverse transform of capital Y, which is equal to little y of t. And now let's just work on this first term, 1 over s plus 2 times the exponential. Okay, I've got table entry 5. I see my exponential. I see my 1 over s plus 2. Coming back to the time side, I see that this should be u of t minus 2. Things are delayed in time 2 seconds times e to the negative 2. This would normally be e to the negative 2t, right? But what table entry 5 says is, yo, that function's got to wait 2 seconds, so shift it over by t minus 2. So what that says is there's an exponential dynamic because of the overdamped mass spring system, but none of that's really happening until you hit it with a hammer at the 2 second mark. So this function, this u function, this step function says 0 up until 2 seconds. And then when 2 seconds happens, this becomes the number 1, leaving you with this exponential function, which has been shifted over 2 seconds in time and is acting as if that's when the experiment started. So then I subtract from that u of t minus 2. But then I have from this second term e to the negative 3t, but I don't want e to the negative 3t because this thing's got to wait 2 seconds too. So I have e to the negative 3 times t minus 2. Okay. So, why were these step functions important? They were delaying things in time. Why did we ultimately want the delay? It is totally normal to pulse systems with energy, a finite amount of energy, over a really short time period, like a surge in a circuit or a hammer hit in a mass spring system. And Laplace transforms tell us that the system does exactly what we think it should, and that is if it was doing nothing before, because of the initial conditions, then when the hammer strikes, it will do its thing. It's just that its thing, which is overdampedness, waits 2 seconds to start up. All right. Questions? Okay. Well, let's go again. All right, 2-minute timer comes up again. Find your y of s function. All right, timer's up. Coming on in with results here. I'm going to just Laplace transform the left-hand side, and then there was something I wanted to say about the ODE before I started doing that, so I'll make some room and kick that up. What do I know? I know that y of 0 is 0, so there's a 0, there's a 0. I also know that y prime of 0 is 1, so there's a 1. All right, so this mass is actually moving a little bit at the start of time. And so that's what the second initial condition is saying, is y prime of 0 is 1. So this mass is moving downwards at the start of time. So if this were the equilibrium or the rest position, the static position, the mass is at the static position, but it's moving downwards. And then if I take the Laplace transform of all this, I'll get y of s times s squared plus 4s plus 13 minus 1 is equal to the Laplace transform of delta t minus pi. And that's just e to the minus pi s according to the transform table. That exponential already is telling me that things are happening special at pi seconds. And that's a hammer hit, right? And that hammer hit's going to add some more energy to the system and trigger some more motion. And that's what I'm expecting to see. So if I solve for capital Y of S, I get 1 over s squared plus 4s plus 13 plus e to the minus pi s times 1 over s squared plus 4s plus 13. This first term here in the Laplace side comes about because of our initial condition. The second term in the Laplace side comes about because of the Dirac function, the hammer hit. So I've got two terms in Laplace side. They mean different things. I don't ever want to combine them. I want to keep them separate. They came from specific places, and that's a good thing. Uh-oh. Okay. I got a little hourglass on my mouse. Okay, only 9 more minutes. We can make it, computer. Let's do it. So, going back to the ODE, what type of mass spring system is this? What classification would you give it? Overdamped, underdamped, critically damped? I can look at b squared minus 4km, so that's going to be 4 squared minus 4 times 13 times 1. And so what sort of number is that? That's less than 0, right? And if it's less than 0, what that's telling me is that this system is underdamped. Okay, and if it's underdamped, what do I expect to see? I expect to see oscillations that get smaller in time until the system comes to a rest. If I'm looking at underdamped, I'm thinking Laplace transforms. Where should I go in my table to look for underdamped solutions?
Recording in progress.
I think he's back now.
Recording
What?
in progress.
What was the last thing you heard me say?
Uh-oh.
What was the last thing you
Uh-oh.
heard me? Oh, really? Oh, that's fantastic. I remember saying that. That's great. Okay. I didn't finally figure it out because I asked the group a question, and then I'm like, they're not answering. They should have answered by now. And then I looked at the faces, and everything was frozen, and it took me a bit to figure out. I thought you were all thinking hard. I didn't know. So, well, back now. Yes. This system, I can figure out b squared minus 4km is less than 0, so this system has complex roots, so it's underdamped. Tell me, where on the Laplace transform table would you go to find underdamped solutions? So to make up for a little time, I guess I'll answer. You want to go to 17 and 18. Woo! Good job, chat. 17 and 18 coming in on chat. Thanks, Connor. And so now that I'm looking at 17 and 18, what algebraic technique would I use to deal with the transform elements in 17 and 18? I don't use partial fraction decomposition anymore. I use completing the square. So now what am I going to do? I've got to complete the square on these elements. How do I do that? I have a 1 over s squared plus 4s. I take this 4 that's in front of the s, I divide it by 2, giving me 2, and then I square it. So that says you should add 4 to this. And then you're like, not so fast. I've got to also subtract 4 to this. Somebody's going to notice that I'm breaking algebra if I don't. And then I add 13, which was there before. But what do you know? That denominator is the same as the denominator on this exponential term. And so I'll just finish completing the square over here. So if I add 4, then these first 3 terms are a perfect square, and they are s plus 2 quantity squared. And then I've got to add negative 4 to 13, and so I'll pick up a 9. So now from 17 and 18, looking at the first, or just this part right here, forget about the exponential part, which one am I looking at specifically, 17 or 18? I'm looking at 18, right? Why am I looking at 18? I look at the numerator and I don't see any s's. I only see a constant. This constant needs to be, well, if this term right here, which is k squared, if that's 9, then my k is equal to 3. And so I need to just forcibly put a 3 in that numerator. But I can balance that out by putting a 3 in the denominator. And I've got to do the same thing with this first term, so I get a 3 in the numerator. And then I've got to balance that out with a 3 in the denominator. And so now these things are ready to go in terms of functions on the time side. So I'll take the inverse Laplace transform of capital Y of s. That will get me little y of t. This first term, which I will underline in green, because of table entry 18, transforms back to 1/3 e to the negative 2t times the sine of 3t. And that might not be immediately obvious from the first term, but what I'm really looking at is the denominator for the second term, because I just kind of completed the square process over the terms because they had the same denominator. Okay, so this is the term, this is the underdamped motion that is the result of this initial condition. So this is the underdamped motion that is the result from the fact that the mass was moving to begin with. This second term here, I will underline in green again. Actually, no, I'll do green actually with hatching. So I can see that. And then, what do? I add on a 1/3. But now when I transform all of this back, this is screaming table entry number 5, which says, do you have an exponential? Check. I have an exponential. What time is that exponential telling you about? That's telling you about pi seconds. Does that make sense? Well, the delta function smashed the mass at pi seconds, so yeah, that totally makes sense. And then I have capital F of s. And then the question is, oh, from capital F of s, what's little f of t? Well, little f of t, that was the first term anyhow. I already had that. I figured that out. So this becomes u of t minus pi. This term is laying in wait until pi seconds. And when pi seconds happens, I hit the mass again with a hammer. And that excites the mass some more. What is excited about the mass is its underdamped motion. And so what do I get? I get e to the negative 2. That would normally be a t, but this function has been shifted over pi seconds in time, so I get a negative 2 times t minus pi. And then I get the sine of 3, not t, but t minus pi, because this is the underdamped motion, which has been time delayed pi seconds, because it is the response of the system to the hammer hit, which is represented by the Dirac function. All right. That is the end of Laplace transforms. There is another example that I have cooked up, but I'm not going to be able to talk about it. I do have videos about that, which I'll post. And so question coming in on chat, what exactly is the u function? This u function is a placeholder for the piecewise function that says, I am the number 0 for all time values before pi seconds, and then I'm the number 1 for pi seconds and beyond, which corresponds to that. The hammer hasn't hit, the hammer hasn't hit, the hammer hits. All right. Well, that is it for today. Have a good day.
Recording